How you guys doing? So continuing off from the previous video with the laser measurement tool, this iteration now uses one of the extracted diodes without the conical reflector on it. I smashed that off. It was a, I'll show it right now with under the microscope, but it is, from what I could tell, it is aluminum and it's encased in glass and epoxied onto the diode, and the surface is actually quite good. Like, it's optically good. Under a 10x microscope with my DSLR through the trinocular lens, like, I couldn't see any scratches or anything in the surface. So yeah, those things are really good. Unfortunately, the beam coming out of these lasers is not a circle, and I can show you that if I turn over here. It is quite a lot more like an oval. It's hard to tell with this because I am reflecting it off something that's not flat, but you can take my word for it, or you can take Google's word. So with this setup, I'm bouncing the laser now off a cylinder that's spinning really fast. And if you couldn't tell already, this is a hard drive that's been gruesomely hacked apart, chopped off on the chop saw somewhere over there, and it's being controlled by this setup here. And this comprises of a, get my hand in here, so this is a ESP32 little development board. This is a brushless DC electronic speed controller, and this is an older one. It's a 30 amp. Instead of a, these things are in drones and stuff. Potentiometer drives back to the ESC or the microcontroller just for development, just debugging and figuring out the speed. So I guess we'll control the speed from 0 to 100%. And the last board over here, this is constant current, constant voltage. I think it's a buck converter. And yeah, I'm using this on the laser, and that's taking the 12 volts. So the yellow and black here, that's 12 volts going in. Red and black, 5 volts. So I'm dropping that down to around probably 5 volts. When I measured the voltage on the laser level, it's 7.6 volts, but I don't need all that power, especially when this thing is so close. And yeah, you can see, like, I'm projecting the beam not in a full 360. It's hard to say, maybe 60 to 90 degrees. So the whole reason why I want to spin this thing is that this surface is not, it's not perfect. Like, it's not optically clear. Like, it looks pretty good there, but on the laser, and even over here on the laser, it looks decently well. But if I set the RPM to 0 on this, that's what the reflection looks like over there. And if I spin it a little slowly, there, so now it's, you can almost probably see the RPM. This is what the reflection looks like. And by spinning this thing up, what I'll effectively be doing is mapping. You see how it starts to stabilize the faster it goes? There we go. Once a full rotation gets mapped horizontally on the sensor, it starts to really stabilize. And I've purposely turned off the smoothing. Maybe I'll turn it on a little bit. With the smoothing off, you can really see like all the noise. So a little smoothing. And as I spin this thing faster, so if I try and sync it up with the camera, that looks like it's 3 or 4. And if I just go all the way, It's hard to say, but it looks like it. You can see the pattern there. So that's applying like that many rotations. I don't know, it could be 7 to 9 maybe. That's mapping the whole thing 7 to 9 times and then averaging out once it gets to here. So really, like, my main limiting factor with the setup is how I can get this thing polished better to get the resulted laser reflection a lot nicer. But the really good benefit of this is, like, even though this is a it's a high quality motor out of a hard drive, like, it's still going to have run out. It's still going to have scratches, obviously, and like there's going to be all kinds of imperfections in the surface. Might not be totally round and everything, but all that doesn't matter as long as it's spinning, because it's taking everything and then averaging it all out. And if you spin it fast enough, you're going to average it out multiple times. Another interesting property of the motor is it's a gyroscope, so it's self-balancing. So any external forces like noise don't really affect it at all, because it's it's keeping stable. One thing with the setup that is showing noise is the fact that, let me get it going slower so it's easier to see. There we go. So you see how the RPM and the shutter, the frame rate of the webcam sensor, like, they're not totally in line. Like, you can see that the left side is rolling, and that is causing noise here, and the noise looks like it's aligning with that. What I'll need to do in some changes to the software is detect and determine this offset and then send it over serial back to the microcontroller, and not rely on using a potentiometer, just using the software to do this. And that way, some other things with this setup is the line itself. So this line is basically getting averaged out by everything as it spins, and theoretically I should be able to get a much straighter line this way. The only thing that really isn't, well, it's quite crucial, is the alignment of this. So I like had this thing roughly eyeballed, and let's see if we can see where it's hitting. So it's hitting the top of this motor, but this laser needs to hit this thing like at the perfect normal of the surface. And if it's not, it's gonna put like a curve in the beam. So getting the alignment of that really good, what I'm thinking of doing is like going with the whole theme of this with hacking stuff. These are, I believe, they're stainless steel, and dimensionally they're in metric, in millimeters. And there's, this stuff comes out of laser cartridges, laser printer cartridges. And this thing it's totally inflexible. Like, I can't flex this thing whatsoever. This stuff would make a good lever for attaching the laser onto the base. And what I'll build is a lever with like a fine adjustment screw on the end, so I can fine tune the angle of the laser to the cylinder. And for a pivot, what I'll use is, if I can pick it up, not this one specifically, because this is out of a laptop hard drive. You can see how small they are, but this has a neodymium magnet on it, and the neodymium magnets, I want to drop it. I'm going to use my left hand because I'm left-handed. So you can see how thin these things are, which is great when height is a concern. And what this is makes as a nice pivot that doesn't have any slop in it. Like, what I can do is take this cylinder, hack off a small chunk of it, and weld it back on, and then I have a magnetic pivot that I don't have to worry about lifting up or shifting around. I can limit its position vertically, and then I could probably make a T-slot or something and use the neodymium magnet as a way to hold it in place, and that way, like, it's not going to go anywhere where it really matters. Like you don't want that the alignment of that thing moving whatsoever onto this, because like any sort of motion, vibration or anything on this side is going to be multiplied out as it goes out. So yeah, it would go, I don't know, something like that, and I'm not sure how long it would be. Maybe 6 inches, maybe 4 inches or so, and that would handle the alignment. The next thing I'll be doing is taking a stainless steel bolt that has a larger ID than the beam itself, and this, like, it's probably 4 millimeters. Like if it's like a rectangle, it's probably like 1.5 to 2 millimeters tall, and maybe 3 to 4 millimeters wide. And what I'll do is take 2 razor blades and restrict just so a small line comes out of this thing, and clean up the beam. Let's get on this side so we can see it. So instead of it being kind of a big blurry blob like that, it'll come out as a nice sharp little short line, and that should clean up a lot of this noise on the extremities here. So it should focus things a little bit better here. So you might be wondering, because I certainly did in the beginning, how to get the alignment of the laser to be perpendicular or normal to the surface here. And the method I've come up with is to use a pointer laser or a laser level, it doesn't matter, some kind of laser, to find 3 points on a line, on a straight line. And the center point, you don't even need to get the center point position to be on the line. You just need to make note of its offset and keep track of those points in physical space. You then have 3 references for a straight line, and with this whole setup you can rotate it. So instead of you looking down like this, the laser, you look at it 90 degrees, so along this axis. And you can see here, so like at this, if we have point 1 here, 2, or 1 point here, 2, and then 3, we align it so 1 and 3 are matching on the laser, and then point 2, if there's a curve in it, it's going to be too high or too low. And then it's a matter of adjusting the angle there. And the larger this is, like if this is like 8 feet, 10 feet, the more accurate you'll get. Like if you're only doing it on a table like this, you're not going to get a very accurate alignment. So if I do it somewhere on the wall or something, or inside, maybe inside the house, maybe that would be a better option. So in the previous video I had a lot of questions and comments about how this method works, and a lot of people saying that you can't do this because you have to get the laser and the surface you're going to measure into alignment. So instead of constantly repeating myself, what I'll do is explain this. So here is 5 or so points. Actually, I think it's like 9 points. Well, whatever, how many points it is. So the slope here is from linear regression, and this is basically a fitted curve through all of those data points, And when you do this, what you end up with is for each point you have a error value which represents its distance from this line to this point. So like if we're looking at this point, we would get this value right here. And if you keep track of all those error values and you graph all that out, you'll get this. And this is correcting for that. So like the line here is just, I've drawn it because it doesn't really matter at all at that point. But this is a way of shifting and removing all of the slope in your data points. And you don't want to rely on trying to get the level or the laser level and the surface you're trying to do level, because like you're never going to get it straight. And like when you're dealing with accuracies in the microns, like that's just not going to happen. You're never going to get it straight anyway. Whereas with this method, you're calculating a virtual line through all that data and then correcting for it, and you're doing it at the nanometers. Like it doesn't matter what the values are physically anymore. It's all kind of math at that point. Another reason why I wanted to use the laser level starting out with was I didn't have a way of producing a laser line, and like a laser level is great because it produces a line, but you can also use it as a laser pointer as well. And for doing the original alignment of this thing, what I did was when I had it on the chair, I used it as more of a laser pointer, where I restricted. I don't think I can do this here, but like if I take, maybe you can see in the shadow here, you see on the blue soldering stand there. So if I make this small enough to be a point there, I effectively have a laser pointer, and I can then get like the whole beam and everything collinear. So by putting everything down the center here, so dusty, and getting the laser over here restricted so it's not producing a line, more of a dot, then I can get that all aligned that way. And then that way I don't need to worry about the quality of the line in the laser level. This whole system does not know the difference between a height change and an angle change, but from doing some math, the angle change is like negligible. So I'm just like, for my purposes, I'm just going to ignore it. And like for the things I'm measuring, it's around 1 micron of error with a slope. And in order, like, there's a lot of ways you could try and get the angle very accurately. Like you can you can take this laser and put a mirror beside it and bounce that beam back to the laser source, and then you can use a sensor. You could even use a webcam sensor the same way, and then determine the height there, and then you'd have to get the distance here. You could get this with using an optical mouse and then tracking its length that way. You can use a laser rangefinder, like a cheap one, and maybe set it up and point it back that way. You could do it sort of like as a black box thing. You could put another, instead of trying to deal with like a whole setup where you're bouncing lasers all over the place, blinding your eyes and stuff. You could build like a pendulum with a tiny wire in a box, black box, where one side you have a LED or even a laser, and the other side you have a webcam sensor, and then you can track the position of the wire on that, and you could find the angle that way. You'd have to let it settle out, but that wouldn't be too much of an issue. But that would give you more of a smaller sort of setup to find very accurately the alignment. But yeah, and for my purposes, for trying to get gantry flat on a CNC machine, like I don't need micron accuracy. I need like tens of micron accuracy. If I can get that surface like 20 microns flat across the whole thing, I'd be extremely happy. So this is where I'm at with this. I got a spinning motor of a hard drive, and I got a whole lot of noise. So my question for you guys is how to clean up the surface. So like this, like I've tried polishing this thing, and that sort of works. This is aluminum, and it was shiny, but it is kind of getting worse. But I need this thing like optically perfect to clean this up. Because brownout doesn't seem to be much of an issue, these hard drives come with stainless steel washers to go between the wafers. And what I could do is take one of those, and like stainless steel is harder, I could polish that up, and like it will have run up because like I won't be able to get it aligned perfectly, but I don't think that matters. So that could be one option. So for now, the main things I'm working on are get this thing better reflected, and get the syncing of the tool syncing over to the microcontroller so we don't get that rolling effect. And those two things should clean up a lot of this noise, because they're, like if we can clean up the noise here, then the rollingness won't really matter. But also if the data is synced, then we get like 5 equally aligned full rotations here, then the data won't be kind of wiggling back and forth like it is. But yeah, if you guys know in the comment section any way of getting these motors, like the surface cleaner, like the best I can think of is putting a microscope glass slide on the edge, because they're quite flat, and maybe some compound and trying doing it that way, and then maybe that can clean up the noise there. But yeah, if you have any better ideas with this, let me know. That's it for this video. If you have any comments about any of this stuff or any ideas making it better, yeah, throw it down in the comments. That's it for now. See you next time.